Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 12 noon on Saturday in Hong Kong. We're broadcasting live from Thousand Oaks, California.
And Pam this time has some cybersecurity news for you.
Let me go ahead and pull it up. I got an email last week, and it took me to this site. Oh, add us to the screen too. And this is really hard to read, so Avada Kedavra. And I went and put together this one. It's actually kind of important, I think. You're going to want to really understand what this is about and what to do about it. So, we got some comments. Hello.
Hey, Cliff.
Yes, we can start the show now.
Hi, Don.
Hey, Don. Welcome.
Hey.
Happy Fusion Friday. Yes. Welcome, Janie. Welcome, Scott.
Yep.
Oh, good. Yeah, me too. But before Jeff launches into that, I want to definitely talk to you about this data breach. And they don't really name this one like they do sometimes, as far as I can tell, unless you know some more about this, Jeff. But it's really going to affect people kind of directly, I think.
Yes,
if I understand. See, this is the thing. I read about it. I found this site. Yeah, go ahead.
I'll give a little bit more detail once you're done here, because
okay,
I do know a little bit more about this one.
All right, I was hoping so. But yeah, they've really done it now. And it's kind of interesting, they won't be able to really find people because you can't do enough to compensate for this. If you haven't locked your credit file, you had better do so right now, they claim. Go to any of the bureaus, sign in, pass the authentication, and then put a freeze on your credit file. Then repeat it the other two. And there's a couple important things to keep in mind here. Freezing, of course, you want to use a different password for every single one of these bureaus.
And not one that you've used for anything else, because chances are real good they have it.
Right. And a little farther down, he mentions that there might be some other folks who will offer to help you with, and yeah, he says don't give them any information at all.
Right, because anyone that you hire to do that now has all of the information that they need. Confirmed. To steal your identity.
They verified it, because it's most likely this particular breach, they're going to have your information.
Okay, does he go into what they got?
Yeah.
Okay, here we go. What's in the breach?
Names, addresses, some phone numbers, dates of birth, and where you've lived for like the past 30 years.
And social security number.
Yeah, that's biggie.
This is everything they need to steal your identity. That's why you want to lock your credit reports.
Right. He said credit file. He did say credit file.
Credit files.
And I supposedly it's in here how to do it.
It is somewhere. So you might want to share this link.
I'll verify how new the data is. So he doesn't know how far back they might find out where you've lived and all the different parts that. Because I guess one of the questions was, where was your last address? Well, that's not going to really help anymore because they got it.
It goes back at least 10 years.
Yeah, he was saying 30.
Yeah,
so
that's likely.
Yeah.
So yeah, all of the stuff that you give to prove who you are, they have. And they don't have it for everyone, but they have it for enough people that it's likely you. It's just.
The odds are good.
Yeah.
The odds are good. So you definitely want to pay attention to this. This is marketticker.org. Let me just grab this address and put it in the. I think you're going to really want to take a look at this. One moment while I get over there. All right, add it to. And we can go back.
Yeah.
So, and then he references this OPM. I was like, what is OPM? Well, I did find out. And this is something that happened in 2015, Office of Personnel Management. That's like the government. But yeah, he's saying this is on a scale similar to that, but not just confined to the government, but to regular folks too.
Mm-hmm.
Yeah. Set up logins, all three bureaus, place a security freeze on your credit report, make all the passwords different. make them strong. I guess sentences are really good.
Right. And we talked about it somewhere in one of my previous ones. 12 random characters or at least 20 letters in a, in a sentence or something. That's what you want for this one. And if you do random characters, a number of places like Firefox, I'm pretty sure Chrome does it too, will create random characters for you. Just copy paste it into a Word doc or something, print it out.
That makes sense.
Put it on a thumb drive or whatever, and just keep it somewhere so that you can have access to it. Because if you can't guess it, they can't, which is why you have to have it,
Yeah. I didn't quite understand this part, the unmasked revolving account numbers. I don't know what that is.
It means that they've got the account numbers for things like home equity loans and credit cards, possibly credit cards, which means that they have everything they need to charge things on your,
Far out. So here it is. One final point has come to my attention. There are a few sites out there offering to check if you're in this data breach. You probably are. That's the point there. Do not, under any circumstances, put personal information into any such site. Nothing ever, period. They probably do have the files, but doing that is confirming that you verified the information for them. So, yeah, not a great idea.
Cliff, hate to tell you, that used to be number one. That's now number 2 of most common passwords.
Oh, number 2. What is 1? 1, 2, 3, 4.
1, 2, 3, 1, 2, 3.
1, 2, 3. No kidding.
Yeah.
All right. Okay.
Yeah. And so that is on the list of what they check. So yeah.
So again, the main point is lock your credit file. Use different passwords. Don't trust any of those offers. Don't give them.
Right.
Don't verify.
Which means
what they probably already have.
Which means that if you do go for signing up for a credit card or going for a loan, you have to unlock your credit files.
Yeah.
Then do it. Then once the loan's done, relock it.
Yeah, that'd be my thing. I would forget. And oh my God, what's going on?
Yeah. In fact, and it'll
lock it, unlock it, just like your car door, just like your house door.
Yeah.
Okay, so to the topic of the evening, it's a crunchy topic. We're going to talk about, Jeff's going to talk about fusion. We'll be back in 8.3 seconds. He's going to talk about nuclear fusion, because if you do a search for fusion, I did this, you'll get something different. Tonight, Jeff is going to talk about what nuclear fusion is and the current state of nuclear fusion. We've discussed fusion in some of our other past episodes because it's what STAR's doing. We actually, we can show you that again, the whole list of other episodes that we've had before. In fact, Jeff was asking about Dr. Greg Hodgin, so he'll probably talk about that somewhere in there, right? Yeah. And a bunch of different STAR things. So it's kind of a lot, but we haven't really talked about what it is, how it works. You ready for that, Jeff?
Sure.
Take it away.
Okay, as Pam mentioned, we talked about nuclear fusion a bunch. And just in case anyone is watching this that doesn't know the difference between fusion and fission, real simple. Fission breaks up, fusion crunches together.
Or slams together, I think, in the case of like particles, right?
Well, they have to.
Yeah.
Because then I'll get into it, like charges repel.
Yeah.
But fission can happen on its own. Heck, uranium is constantly popping apart. But fusion can't happen without an outside force acting. And in the case of stars, it's gravity just crunching everything together. In the case of reactors that we're trying to build, it's heating it up and sliming it together.
Usually in a cyclotron, right?
Yeah, that's the most common way that we're
Tell
trying.
me when you're ready to share. I see it up there, but
yeah, go ahead.
Okay.
Nuclear fusion is reaction. I'll just really quick. Anyone can read the wiki. This is just two or more atomic nuclei, usually deuterium and tritium. Note, that's for human generated. Combined to form one or more different atomic nuclei. One of the things that I learned elsewhere, not in this article, although I think it's here too, is that there's two types of fusion.
Mm.
One, the type that we use to generate power here, is basically combining two nuclei into a bigger nuclei.
Okay.
You know, two hydrogens into a helium.
Yeah, that seems.
The type that happens in the middle of the star is conversion.
Mm.
It converts a proton to a neutron as part of the fusion.
Oh.
Yeah, which has surprised me. And
okay.
So let's look at.
Am I sharing again?
Yeah.
Okay.
And this is where I learned it. I actually saw this before I saw the wiki, because I figured everyone reads wiki. There's two types of fusion. And this is deuterium plus tritium produces helium and a neutron. That's
deuterium.
Deuterium, yeah.
Yeah.
This is what we use in most of our reactors. The sun uses hydrogen plus hydrogen. No.
Yep.
Single neutron hydrogen produces deuterium and a beta particle and
a photon.
No.
Okay.
And this is a positron, not a positron, an antiproton. No, okay, it is a positron. So it's an anti-electron. So it's a positron.
Yeah, that's really small.
And a neutrino.
If you can bigify that, it'll be easier for people to see. Yeah, that's better.
So positron and a neutrino. So that is not, but you notice that they make a lot of news about the neutrinos that the sun gives off. And this one produces neutrons, not neutrinos. So man-made does not produce neutrinos.
Interesting.
And
well, neutrinos are from everywhere. They're constantly
because
through us.
They're being produced by stars.
Okay, because I heard sun. So it's not just our sun, it's all of them.
Okay. All of them everywhere, yeah.
All right. And they've been around for a long time.
And the reason is this reaction gives a lot more energy, but it also is very hard to do.
Okay.
You can't really do it without the entire mass of a sun crunching things down.
So it's a big gravity thing.
Yeah. And you put enough mass together and it happens, quote, for free. You don't have to put the energy into it. Yeah.
I think it takes a while for it all to swirl around and then ignite. But you get enough mass together and it will. Got it. Because I guess it all collapses in on itself.
Right. Yeah.
Okay.
And so this is, and I saw, so this is normal. Well, okay, this is Earth fusion. This is what we use in our power plants. Okay. Deuterium, tritium produces a neutron and a helium and some energy. Okay. No, often gamma rays. But it produces heat and energy. Nice diagram. Good. Yeah. This is the diagram of what happens in the sun. Basically, two heliums produce a helium-2. Or no, two hydrogens produce a hydrogen-2. Sorry. Got it. It's basically an ion of hydrogen, right? Right. Basically, no. It's a neutron. Basically, one of these protons converts into a neutron and a positron, thus maintaining balance of charge. Okay. And it gives off a neutrino, which, unlike a neutron, just zooms out of there. Now, does this positron last very long? Likely no. Okay. Probably hits an electron and produces more energy. Chain reactions? Right. Okay. And then helium-2 plus a helium-1 produces helium-3 and a gamma ray. Helium or hydrogen? Or hydrogen 1 and hydrogen 2 produces
Okay.
a helium. Sorry.
Okay. It's all hydrogen, right?
Mm-hmm. There. And this process happens again. So you take 2 helium 3s, they fuse, they give off 2 protons, which is essentially a helium 1 and a helium 4. And this is the end state. No, you've got these 2 protons, which then feed into half of this equation again.
Hmm.
So
oh yeah, it looks similar.
Yeah. So
so a lot of it's like all these reactions within the sun.
Right.
Well, any star.
And
really.
it pretty much stops at helium 4.
Okay.
Until it essentially runs out of
that one
hydrogen.
Is helium.
Yeah.
Okay.
He.
Yeah. Yeah.
And the main reason is because fusing helium 4 into something else takes a lot more energy. And so the cheaper stuff is going to happen first.
Okay.
Nature basically generally takes the lowest hanging fruit.
Yep. Makes sense.
And this happens in the core. And so you've seen this before when I talked about stars. The yellow, the one in the middle, is the range where our sun is. And basically all of this happens in the core. No real fusion, although some does happen out here. But this is all convection.
Okay.
One of the things is that all of those gamma rays produced by the core, the sun does not give out gamma rays very much because it takes about 30 years for a photon to get from the core out to the surface of the sun, just because it keeps hitting things. And every time it hits things, it gets absorbed, re-emitted, loses some energy, and drops down slightly in its frequency. So by the time it comes out, it's in the visible light range.
Okay.
And
that's a rough road. 30 years to go from the core to out.
Yeah. Now, the hotter the star, the more of them actually escape in the higher frequencies, including gamma rays.
Oh, interesting.
Just basically, they get out faster than they can be absorbed and reabsorbed.
Okay.
So that's what's going on in the sun. And here's some news. I didn't want to get to that yet. Here, where is it? Did I lose? Did I lose my? Oh, I lost one of my things. That's.
I hate it when that happens.
Oh no, this one.
Okay.
Here.
You had to go back.
This is a PowerPoint.
Oh, I see.
This is the fusion into heavier elements. They don't. Unfortunately, I didn't find one of the path up to carbon. But from carbon.
I forget the exact sequence, but there is a sequence of things that start burning up all the way down to iron.
Right.
Anything heavier, we get it because of a nova or supernova, really, right?
Right. Nova or supernova, yeah.
Either one? Okay.
Or neutrons hitting each other produces a lot of the heavier elements.
Okay.
But because this goes all the way up to silicon.
Okay.
So this is what happens in the main sequence of a star, or as it hits, the later sequences, because this carbon, nitrogen, pops up. Here's and so it goes, and then this is what happens at the higher ends of it.
Okay. These are basically fuel for the star.
Right.
Starts with hydrogen, and then helium's next for sure.
And then
and heavier and heavier things.
Yeah. And here is oh no, that F was fluoride, I think.
Fluoride?
Yeah.
Okay.
Or fluorine or something. But yeah, so this is all in the main sequence of a star. But as you see the colors, I think they're color coding it for the color of the star as it's happening, but I'm not positive.
Oh, okay. So the star goes through a life cycle, and it also goes through these different elements.
And the reason
why
is that they've got threshold energy, and this is the binding energy, and this shows helium 1, helium 2, helium, or hydrogen 1, hydrogen 2. I keep doing that.
I did too.
Helium 3 is actually easier to get than hydrogen 3.
Interesting.
I mean, and then it goes up to helium 4 here. And so that kind of ends that chain. And then it
Can
confuses.
you click on that to make it bigger than
Yeah.
Yeah.
Actually, no, apparently.
Oh, that's weird.
Well, there we go.
There we go. Eventually.
So, so helium 4 is up here. So that's the end of that chain. But then when it gets hotter, you can produce lithium, and it starts another curve up here. Oxygen, iron is here. Then you start seeing decreasing returns. You have to keep putting more energy into it, but the energy that you get out of it starts going down.
Okay. And this is basically the end of the life of a star at this point.
Yeah, when it hits iron, yeah,
it starts to decline.
Yeah,
and die. Stars have birth, life, and death.
And we've talked about that when we talked about stars.
Yeah.
I just wanted to hit on this because I saw this in the fusion thing of this is what's actually going on. This is why. And this, I think, biggest naturally occurring elements that we generally find, in nature. Most of the heavier ones have a half-life short enough that they're mostly gone by now. But so when you get up into here, you've got fission going on. Here is, I looked at, and I'm going to pop this. This is the Fusion Industry Association. So
oh, cool.
These are all the articles that they gathered from.
Oh, so they've curated from
yeah,
other places. Okay. Nice.
Man. I saw this and I thought it was IKEA. And I'm wondering, what the heck is IKEA talking about it for? But okay.
Not quite.
Right, yeah.
Oh, Japan even? Wow. Good.
Yeah.
That looks very, very helpful.
Yeah, so I am going to, anyone who wants to know current news,
so
I'm going to post this here.
And that should show up as a clickable link unless it's really long.
It's not.
Oh, good. Yeah, that should work.
Okay.
Nice. And I'm sure they keep adding to it, right?
Right, yeah.
Yeah, look at
this.
Like
August 20th.
Oh, yeah, that's really recently.
And you'll see, probably in a number of these, you'll see, oh, it hit a new milestone or broke a new record, because of course they love talking about that.
Sure. Why not?
And this is phys.org, and I just searched for nuclear fusion. They talk about it. Okay, this one, researchers dig deeper into stability challenges with nuclear fusion with mayonnaise.
What?
Is
that like a buzzword for something, or do they mean mayonnaise?
I just found this afternoon.
It says Hellman's Real Mayonnaise right there, still helping us in the search for solutions. That is awesome.
So look at phys.org. They'll have this. I don't know if mayonnaise is the target. Okay, so whatever.
I love it.
U.S. perfects lithium vapor cave. Okay, this gets into one of the problems that we have with man-made fusion is that you produce this energy, you produce this heat. Now what?
Use it.
Well, use it fast, because one, it escapes through the machinery. 2, use it fast because it escapes through the machinery, and the machinery doesn't like that. So you're cooking your reactor at the same, So they're using what they're calling a lithium vapor cave. Essentially, they're basically melting lithium, heating it to a vapor, and then and that soaks up the heat to protect the equipment.
Interesting.
And then moving that vapor to somewhere where they can extract the heat from it.
Hmm.
So it does two things. One, it protects the reactor itself. In fact, they talked about, a +1 on this is using a porous medium on the surface of the reactor, and then just pouring liquid lithium, which has a fairly high melt, which you have to melt first, but if they've got plenty of heat so they can do it, through the porous material, and the hottest spots will evaporate more. So you don't have to calculate where do you need it. You just pump it through and it'll evaporate where it needs to.
It's an elegant solution.
Yeah. I mean, if everything's tuned right, it evaporates evenly. But if it's not, then okay. And things change. I mean, things get hotter, some spots might get hotter than others and warp slightly, and that would produce, someplace that a hot spot on it. So
here's a weird question. When the lithium batteries are done, can you send them over there and they can use it for their
possibly
sink in their reactor?
But
like I said, it's a weird question.
Because the
thought of it.
main problem that we have with nuclear fusion is getting the energy back out of it. And they've broken even.
Actually, they are broken even. Okay.
But that's a great
start. I mean,
yeah, it's a great start, but it's just a headliner at the moment because we're clickbait.
Okay.
To use the more pejorative term.
Better than comics.
Right. Because they basically are producing as much heat. Heat energy equals that electrical energy that they put into it.
Okay. Now,
that heat, what do you do with it? You have to get the electricity out of the heat. And since it's not 100%, and since a lot of the heat escapes, that's what this, liquid or this lithium vapor is trying to solve. It's trying to capture as much heat as possible and get it away from the machinery.
Got it.
So
there's always going to be loss. I mean,
right. Yeah. But you have to get the loss down to, just like they keep ramping up the efficiency of the coils. In fact, a couple of weeks ago, we talked about them doing a braid instead of just a donut shaped, track, doing a twist to it. And that's slightly more efficient. If they get slightly more efficient enough, they'll be producing enough energy for the energy. Then they have to do slightly more efficient enough of turning that heat into electricity. They have to work both sides of it to make it viable.
Got it.
And to produce enough electricity that it actually matters. I mean, if you get 1% more electricity out of it than you put into it, that's nice. Doesn't do much for you, but that's nice.
Okay.
It really isn't worth the amount of money, energy and stuff that it took to build the darn thing. Then you say, well, you just need to do it in scale. Well, okay. You cover California in them, and you can power the US maybe if it's that inefficient. So it has to get efficient enough to be useful.
Okay.
So that's.
Am I sharing again?
Let's see. Yeah. This is
yes. Okay.
Yeah. This is another search of a site that I found a few weeks ago. This is Interesting Engineering.
Oh, looks cool.
This search isn't quite as good, but this is where I found the lithium vapor cave. But then they also talk about solar farms, etc. So their search engine is not quite as good as phys.org's.
Got it. But still, those look interesting too. Yeah.
They're talking about using different alloys in the fusion breeder blankets. This is basically keeps the heat in and off the equipment. Nuclear container ship. This is actually fission, not fusion. Again, molten salt reactor.
Oh yeah.
This is fission again, but fusion reactor created by a school teenager successfully achieves plasma. No, not fusion, but plasma.
Okay.
And let's show us, because
Yeah.
here are the things that basically prevent fusion in nature. One, you've got an electron shell around each of them.
Right.
And they repel, since minus repels minus, they repel each other. So you have to either strip the electron shell off, which gives you a plasma, which is why we use plasmas, and you get enough heat in the shell comes off anyway, which is why the internals of the sun are plasma.
Okay.
So plasma's easy.
Okay.
But otherwise you have to get them close enough. You have to hit them hard enough to get close enough to get through the electron shells.
Yeah, because it's one of the forces, right? The electromagnetic force.
Which is what there was a big thing on cold fusion in the 80s, 90s. I forget, it's long enough ago, where they were saying that they could use chemical catalysts to do that. And it was just basically someone producing bogus stuff to get known. Because
you're going to be known for the wrong thing, I think, but okay.
Well, you got
15 minutes of fame.
Yeah, you got your paper published, and now you've got your PhD, and you thumb your nose at everyone else.
Okay.
But so once you're either past the electrons or you've stripped them away, now you've got two much denser positive charges going to each other. And so instead of this diffuse electron charge that, you have to, push yourself past, you've got two. So it's like having two weak magnets and trying to push them together. You can. Now, since the nuclei are more dense, they're like really strong magnets. Now you're trying to push those together, which is why it doesn't happen in nature, because for one thing, the electrons will probably deflect them enough so that they won't, even if they're going fast enough, the chances of them hitting just right to get through the electrons without being deflected and then hitting each proton just right. I mean, it might happen like out in space once per, millennia or something like that. But that's not a reactor. That's just, oh, look, that happened. That's weird. But so once you're past, you have to then hit hard enough to get away from that repulsion, and then hit hard enough to actually cause them to combine, and then break apart.
A lot of hurdles there.
Yeah, which is why the mass of the sun or any star is a nice, cheat. Essentially, it crunches it down so hard that they don't have there's nowhere for them to go. It's nowhere.
Yeah, a lot of pressure.
Yeah, a lot of pressure. Everything's moving fast. And since everything's so close, it's better chance of them actually hitting and combining. So the inside of a star has lots and lots and lots of hydrogen or helium or whatever. So lots, target rich environment. Plus it has the pressure to basically make it more likely.
I think they talk about it in terms of gravity versus like gravity in and pressure out.
Right.
And once it reaches equilibrium,
well, yeah,
it's a stable star.
Yeah.
And if it's got one or the other, it will either explode or it'll implode.
Well, it'll usually expand until it reaches stability, because as it expands, the pressure decreases. So, gravity essentially exerts pressure in. Heat produces pressure out. So, a star is essentially the size of a star is where those are in balance.
Yeah.
It's when things change that, that stuff happens.
Yeah, like it burns up its fuel, or it's
white dwarf,
or it gets like there's the T-core board going on right now. I don't think it's done its.
Yeah, I don't think we
haven't.
Yeah, I think it would be 2 in the news.
Yeah, I think we would hear about it. And we had a guest talk about it a few weeks ago. And this is where a companion star is feeding it. So it's gaining more mass, and at some point it just blows it out again.
Right, yeah.
So,
it layers onto a neutron star. Yeah,
There's
or
a few
white
of those
dwarf.
in the
Yeah.
that we've noticed in
Yeah.
the universe.
Yeah.
Cool.
So,
Do you have more
um,
tabs to work on?
just a couple.
Let me show them.
Where do we stand on fusion technology? This is IAEA.org. Who are they? International Atomic Energy Association.
Cool. Yeah, that sounds familiar.
And they have a video that talks about the difference between fission and fusion. But essentially, fission gets energy by breaking apart. Fusion gets energy by slamming together. You know. So the tokamak reactor, that's the donut reactor that everyone talks about. ITER is kind of a variation on the tokamak. Now, one of the things that they don't talk about, and Greg Hodgkins talked about it before, because here they're spinning it, heating it up, and colliding them to get it. Another way is you get a bunch and you compress them down somehow. And in the 90s, they talked, there was one scheme to use physical rams to hit water or some substance. Water doesn't compress, so it's really good for this. Hit water to the point where you've got a whole bunch of waves going through the water and put the point where all of the waves peak right at the center to produce the pressure. And
I remember hearing about this.
Yeah. And
I don't know specifics, but
it's a good idea, except that it's so mechanical that there's so much to break down. They all have to hit exactly right. Otherwise, the peak is not where you want it to be.
Hard to do.
Or too diffuse to do it.
Yeah.
So they have to keep it continuously tuned, continuously slamming super hard, which those two are kind of incompatible. So it takes a lot of tuning. There's going to be a lot of mechanical wear.
Seems like with computers now it would be a little bit easier.
But still not
easy.
Yeah, still not easy. It's the steampunk method of fusion, which is why I was interested in it, which is why I looked into it so much back then, because that'd be really cool. I mean, and they were steam-driven rams to ram into the water. And
wow,
where do you get the energy for the steam? Well, from the fusion. So it was basically once you got it going, just bam, bam, bam.
Perpetual motion machine.
Yeah. So that was, well, not perpetual motion because you'd still have to feed it the hydrogen.
Oh, okay.
But it was still like that made me so happy. And then it's like, that's not going to work. I mean, it made me almost as happy as the thought of cold fusion, because that would have been perfect if it wasn't physically impossible to happen. But, hey. And then Craig Hodgkin talked about Hodgkin. Sorry.
Okay, and then I kept doing that too.
Yeah. Craig Hodgkin talked about, they're talking about creating not warp drive, not Star Trek type warp drives, but similar, but shorter duration, much smaller.
Much smaller.
In fact, so small that you can throw a few hydrogen in there, create them all around it for a fraction of the cost of, say, moving a rock. And
yeah, it's really, really good episode.
Right. And you might be able to do enough to fuse the
you okay?
Yeah, I'm hearing something, but you might be able to get enough pressure that way to fuse the helium or hydrogen or helium and get enough energy out of it to run the machine.
Okay.
So that's another method that doesn't involve
there it is.
That's what that was. I knocked the phone off. It doesn't want to stay there. Okay, there. Move my keyboard. So that's just another method. It would potentially be more spaceship friendly if it works. Because you wouldn't have this ring of plasma that if something breaches the ring, you basically have a blowtorch going through the ship. With anything that causes compression into a central point, if something happens to it, it stops working. And so then you've only got the heat.
It's a better
that is producing, and
Yeah.
so it feels safer.
I'll have to write to him again. I did send a couple of emails and asked if he could come back or someone on his team could come back, and haven't gotten that happening yet. But I think I'll ask him. You want me to share again?
Well, they only talked about the ones that they're building, so that's all they talked about for it.
Okay.
But I'm gonna give you this one too, because this is another source of news that would be potentially good for you.
Awesome.
So,
and that should be a clickable link.
Yep.
Not too long, so it didn't break.
Yeah.
Yay.
So, and then
it looks like you had another tab over there.
Did I?
Is that one or?
Oh, it just talks about new record, but there's always a new record.
Oh, okay.
So it doesn't make me excited until they say they got enough electricity out of it to run their own reactor.
Okay, and then of course you have to duplicate it somewhere else too. So
right,
it's not real until somebody can do that.
Yeah,
it's not just pictures for the
quite
science.
Frankly, I'd be thrilled to see them light a light bulb. Off of it. I mean, that was
if you can do one, you can do two, and
right, exactly,
so on and so forth.
Yeah, because so far all they're doing is making heat. And you can do that with just about anything.
Rub two sticks together. You got heat.
Yeah, so you have to do something with it, and that's why I like the lithium vapor, because it's actually a solution to one, get the heat away from where you need it or where you don't want it,
right?
Put it where you can use it.
Yeah.
I mean,
I hadn't heard about that, so very cool.
And quite frankly, you could run a piston off of it directly.
Yeah.
So.
Yeah, he can be run. You got to be able to use it, but.
Right. Yeah.
Yeah, he can do a lot of things.
Yeah. So. There you go. I think that's it for fusion.
Okay.
There's a. Do you have in our listing the search for fusion, all of the articles that we've done on fusion?
Yeah.
Okay. Yeah.
Yeah, it's real simple. You go to the top here where it's got the little hourglass or
spyglass.
Yeah, and you write in fusion, and all of the articles, including this one, obviously, came up.
Yeah, and Greg's is really good.
Yep.
And we talked about fusion a lot because we talked about stars a lot.
Yep.
Do
you have any stars left to talk about?
I'll have to look because I think that there were some. I've just forgotten what they were.
That's quite a few.
But I've got most of the big ones. There's some few that are like half this, half that. That sort of thing that I could talk about.
Okay. Well, maybe someday. So stay tuned.
Yep.
All right. Ready for this part?
Sure.
All right. Some stellar events this week. We're talking about August 23rd through August 30th. August 25th, the Uranus and the Moon are in conjunction, and the Pleiades star cluster is 0.1 degrees south of the Moon, and we saw the word occultation, but they didn't say
where
you could see it. Actually, we saw some really nice pictures on Facebook of the last one was Saturn and the Moon. I thought that was really, really neat. And I don't think those people were in exactly the places that you rattled off where they could see it from. I thought they were
right
a little bit, well, I don't know, it's probably a whole area. So August 26th is the last quarter moon, and Globe at Night starts a new project. Oh, I got that. Let me go ahead and set that up, and go ahead and share.
Okay.
So we're talking about August 26th through September the 4th, and as you can see, it is Cygnus in the north and Sagittarius and this is the southern hemisphere. Northern hemisphere, southern hemisphere. They only give you one this time.
Oh, you're not showing.
Yeah.
Cygnus? I don't see Cygnus on there.
You gotta look at that.
Oh, okay, yeah.
I wanted to look at the notes.
Okay.
You can stop sharing.
Okay.
Thank you. So go out, look at your area, and find either Cygnus or Sagittarius, depending on which hemisphere you're in, and go ahead and report to the site because this is a very, very huge citizen science project that helps them understand the night sky from people's locations, and it has to do with darkness, light pollution, that kind of thing. Very important, I'm told. All right, August 27th, Mars and the Moon are in conjunction, and Mars is in fact 5.3 degrees south of the Moon. and Jupiter and the moon are in conjunction. Jupiter is 5.7 degrees south of the moon, so they're all going to be like together.
Yeah. Now it depends because they could be in different angles off of the south of the moon. So Mars and Jupiter might not be actually in conjunction, but they'll be nearby.
So let's see, where are we? Oh, also Mercury appears stationary. August 28th, the moon rides high. Don't say it. August 29th, Pollux is 1.7 degrees north of the moon. And we're back to Friday night show, the August 30th. And I'm going to prepare for, we'll tell you in a bit. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel. What inspires you the most for the coming week?
Okay, if you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. Join us again next Friday, August 30th. We're bound for the stars. Will you be ready? Pam wrote a 4-part article. I saw A4 and I was thinking, we don't use that paper. Wrote a 4-part article on the Everyday Spacer blog about preparing yourself for space travel. Next week, she'll dig into that a bit and see if anything has changed since the publication of those articles.
Yeah, that was quite a while ago. I started the blog in 2012.
Mm-hmm.
So I bet a few things have happened since then. And certainly it has become easier and easier to go out there, to do cool stuff in space.
Heck, what is it, 200 grand now will get you out there?
200 grand, really?
Yeah.
Oh, I hadn't seen that. Wow. Very cool. So, all right, shout out. Cliff was here. Yay. Scott was here. Janie was here. Dawn was here, and we are so grateful for you every time you show up. Thanks so much. It really makes a difference for us. We have a lot more fun, for one thing. Oh, Cliff said something else.
Oh,
where is he?
Here we
go. Got it?
Yep. Interesting topic, as fusion would be the energy for intergalactic travel in the future and save the planet. And what about Mars? Yeah. Well, yeah, because solar power doesn't really work so good on Mars because, of course, it's farther away. Got dust, etc.
Yeah.
So if we can make fusion work here, we can make it work anywhere. It's just the first rounds of fusion that we'll make will probably be too heavy to put on a vehicle.
Oh, okay.
But
you can build stuff out there. I mean,
you can build stuff out there, but yeah, but then you have to still move it if it's super heavy. So it has to be even stronger, which makes it even heavier. It gets, it's the rocket equation.
Oh, Janie has all. Yeah, have a great week. Okay, thank you, Janie. You too.
Yeah, you too, Janie. Yeah, so, yeah, I definitely want to see fusion, perfected. Get it small enough that we can put it on a vehicle, even if the vehicle has to be large. That's
okay for me.
Yeah.
As much as I want to go out to space, I am claustrophobic, so I want a really big spacecraft.
Or learn how to breathe vacuum, and then you can ride outside.
That's something else. That's a whole different thing. All right, folks, have a really good week. Thank you so much for being here. Anything else from you?
No.
We will continue to watch for your comments, and see you on Friday.
Good night, folks.
Good night.